fai qua sentiamo se arriva l'audio con il microfono.
Poi
sì, in effetti è un po' troppo lento. Bisogna vedere un attimino poi la funzione.
Allora non è questo, è questo, ma questo è stretto.
Anche questo è stretto. C'è una cosa sopra di quello.
No, non è vero. Dammi il microfono. Pronto? Pronto? Marco, ma stai verificando sul computer? Prova a mettere il rec. Prova.
Bear with this. Thank you very much for making it. That is a nice place.
L'hanno spostato. Dovrebbe esserci un telefono. Pronto? Pronto, pronto? Mi scusi. Sì, poi abbassiamo tutte le luci. Sì, le finestre, la porta.
penso che sono quelli che filmano che vogliono più perché
no,
è proprio di fronte, quindi
se no non si vede bene. Prova su quello, perché potrebbe essere un problema del computer. Vabbè, sul canale Google Plus di NAV, la Yacht è già aperta. Prova.
solo quello ambientale.
Sente l'ambientale, quindi il problema è il microfono. Non lo sente per niente, vero? No, ma il radiomicrofono è aperto? L'hai preso?
Alessandro,
Così tanto arriva? Allora lo prende comunque. Arriva. Ok, va bene. Io sto là. Sono uno e Bino. Senti Marco, dove lo teniamo secondo te? facciamo così, vado a prendere lo scotch. Vado a prendere lo scotch,
Ok, ho paura che vogli giù.
Pronto? Così non mi va in distrazione, così non meglio. Sono un grande piacere di essere qui.
Buongiorno a tutti. Ho venuto qui a Montemario, una visita estremamente importante per noi. Sua Eccellenza l'ambasciatore del Cile, che per la prima volta, mi pare, viene a visitare questo luogo che ha una fortissima storia, però noi cerchiamo di portare avanti l'astronomia di oggi e domani, e lo facciamo moltissimo in collaborazione con Cile. In collaborazione sia per il sito geografico, che adesso poi vedremo, perché vi farò vedere qualcosa di spettacolare, ma anche culturalmente abbiamo sviluppato come Italia e Europa dei legami con il Cile dal punto di vista scientifico, culturale molto profondi, e per questo le do profondamente il benvenuto qua. Se ci vuol dire magari due parole, poi tenteremo di fare un po' di presentazione su che cosa vuol dire fare astronomia. Prego.
Buongiorno a tutti, soltanto dire due parole per ringraziare innanzitutto a questa istituzione per questa collaborazione con l'ambasciata del Cile. Dire che questo è un primo incontro che abbiamo, e grazie anche a Maria Teresa Ruiz, astronoma dell'Università del Cile, che è stata invitata per la settimana dell'astronomia che si è organizzata a Milano, all'Expo Milano 2015 al Padiglione del Cile. Ho avuto l'opportunità di sentirla la settimana scorsa, è stata una bella presentazione con l'ex direttore capo di Massimo Tarelli, che è stato a Milano, e hanno fatto una bellissima presentazione. Vorrei dire che fra pochi giorni in Cile sarà il primo capo di governo italiano, Matteo Renzi, con una delegazione, e che è lui invitato ad andare a Paraná, farà una visita il 23 e 24 di ottobre, e siamo contentissimi per quello. È un fatto molto importante, una mostra di interesse per il sviluppo scientifico dell'Italia, della cooperazione con l'Unione Europea, con l'Osservatorio che sta lì, e con Cile. Finalmente vorrei ringraziare particolarmente a Maria Teresa Ruiz per questa visita. Siamo molto contenti di avere l'opportunità di ascoltare cose molto interessanti dell'origine di dove proveniamo. Un'ultima cosa: in Cile si fa a gennaio il congresso del futuro, organizzato dal Senato cileno. Questa è la sesta volta che si fa, è un incontro particolarmente importante perché di tutto il mondo arrivano scientifici di diverse aree, premi Nobel, eccetera, eccetera, per 3 giorni discutono molto è questo? Gennaio dal 15 al 18 mi sembra. Invieremo un programma. Questo anno abbiamo 2 o 3 italiani che vanno a fare la presentazione di diverse aree, e sarà una cosa molto interessante. Grazie mille.
Grazie professore. Prima di dare la parola alla collega Ruiz, permette che le presenti è l'uomo più grande del mondo e del cielo, è la versione, la presentazione dello Extremely Large Telescope, e dopo farò vedere anche la location dove è stata. Anche per la signora avevo pensato questa immagine del cielo con spiegazione dietro. Questi sono i tipi di lavori, di osservazioni che si fanno dall'ESO, l'Osservatorio Europeo, a quale l'Italia partecipa. Grazie, signor Presidente. Io le consiglierei di sedersi per vedere meglio. Anch'io vado. We have to decide which language. We have to make a poll.
Sì, posso farlo in inglese o in italiano? Show hands.
Show hands, who wants English?
English. Quanti sono? 1, 2, 3, 4, 5, 6.
Maggiore.
C'è qualcuno che non capisce italiano?
Sì.
Non ti capisco l'italiano.
No, abbiamo una visitatrice, pardon, Patricia Kelly from Australia just arrived. No, she doesn't. Neither Italian nor Spanish. If you do it in English, I think it's better. It's all right.
Okay, no, actually it's easier.
Yeah, actually, I think so. I will do it in English.
Well,
The slides.
The slides, I'm going to give them in Italian. I have them in English too, but
That's okay. We'll learn some Italian now.
Okay, well, c'è il microfono o
C'è il microfono.
magari non è no? Ahí? Este?
Quello lì va benissimo.
First, I would like to thank the invitation to be here, to enough to host this talk here and in such a beautiful place. I discovered that we astronomers always manage to work in really spectacular places. And also to the ambassador here, to the Embassy of Chile, that they have invited me to give this talk. I warn you, this is not a talk for specialists, it's just a general talk. And as I say here, this is a talk on the history of the universe. But let me start with this question, why Chile? You know, even in Chile, sometimes people say, why Chile is such a special place for astronomy? Really, what is considered to be a window to the universe. And why all of these observatories came to Chile? First, because it is in the southern hemisphere. If you see the Earth, in the south, there's very little land. You know, all the continents and the civilizations have been in technological civilizations have been in the north. So and it's what you can see from the northern hemisphere is different than what you see from the south. Well, you from Australia know we have the best guys, and in the south there are two really fantastic astronomical objects that we want to know about. Is the center of our galaxy is in the south. In Santiago, it is just above our heads. And the two satellite galaxies, the Magellanic Clouds, that go around our galaxy, they are really at a very southern declination, that is -70, -60. Even from the north of Chile, you can tilt the telescope quite a bit to see it. From the north, they are invisible. So this is one reason. We have clear skies, a region of between the second and the fourth region in Chile. In the north is very, almost every night is clear. And we have a lot of mountains, really high mountains. And you can see this is a geographical reason to have this special situation. This window is really unique in the world. And this is due to the Humboldt current, which is a cold current that goes all around the Chilean coast, coming from the pole, and that promotes the formation of clouds in the ocean and not in the continent. And then we have the Andes, which are very high here, who prevent the humid clouds coming from the Atlantic to cross over. So we really have a special situation there. Here, some of the European observatories, the VLT, I will show, and ALMA are there. There are some other observatories further south. The first observatory in Chile was founded in 1852 in Cerro Santa Lucia, in the center of Santiago. Now you cannot even see the moon there, probably, because it's completely surrounded by lights and traffic. But at that time, it was probably a little bit outside the center, and these are the constructions of the first observatory. The Cerro Santa Lucia doesn't look like this now because it's been transformed. And then the next important step was in the end of the 1950s, and when the University of Chile and Cerro Tololo Inter-American Observatory signed an agreement to create an observatory. And these are the very comfortable places where the astronomers had to be at that time. This is one of the University of Chile astronomers at that time, when they were measuring the seeing conditions of the place. After that, the mountain was cut, and then the observatory was installed there, and it's been operating in Chile for the last almost 60 years now. And this is a 4-meter telescope, At that time, in the 70s, telescopes were huge domes. Now you will see they all becoming smaller because you want to have. The idea would be to put the telescope in the middle of nowhere, nothing around, because you don't want to have difference in temperatures that will produce turbulence. And, but you can't because there's dust and maybe some rain. So but they build these huge things that are complicated because they become very hot and then they cool down during the afternoon and there is a turbulence inside. That's why they open windows here so that the air will flow through and everything hopefully will become the same temperature before the observing. In front of Tololo, there is a mountain, a little hill, it's a mountain actually, it's almost 3,000 meters high. Cerro Pachón, where you have a Gemini Observatory. The other one is a national optical observatory from the US. This one is a mix of countries, and it is an 8-meter telescope. It's a more modern one, and you can see the dome is smaller, although the telescope is much larger. And it's called Gemini because there is another one in Hawaii who looks the northern hemisphere. And in that mountain, there is a project that is started already, the construction, LSST. This is an 8.4-meter telescope that has a very wide field of view, and it will take pictures of the sky every night. It will take 3 nights to cover the whole sky, and the fourth night, it will start again. So anything that moves or change in luminosity will be discovered. And this is opening a new window to discovery, the window of time, everything that moves or change luminosity. And there are many partners here, just to show these two is the Department of Energy, National Science Foundation, but there are partners like NASA, because they want to detect any possible object that could be dangerous to Earth, like a comet or a big asteroid that they want to discover it very far away so they maybe can do something about it. But also, what to me is more exciting is that Google is one of the partners. So Google is going to put all of this data. There is going to be 30 terabytes of data every night. So that is a challenge to be able to transmit and process all that. But when it's processed, it's going to be put in the web, in Google, so anyone in the world can use this data. And for the first time, astronomy is going to become more democratic, because astronomy, it's always been the science for the rich. Even in the old times, the rich, the millionaires, they could afford to be astronomers. And even now, rich countries, many of these instruments are millions, hundreds of millions of dollars. So, a small country like Chile could not afford it. Not even a large country. Now they are this consortium of countries. And so this data is going to be there for anyone with a nice idea. It could be from a town in a small country. They can download, just have an internet connection and do research. This is fantastic. It's going to optimize human intelligence. If you go a little bit north, this is La Silla, the European Southern Observatory, the first observatory they had in Chile. This is the largest telescope, the 3.6-meter telescope. I am particularly fond of it because I did most of my research there and some really exciting discoveries. And then the 3.5-meter telescope, which is much more modern, and you can see smaller because they realized they have to make it, the dome, much smaller. There are a lot of other smaller telescopes, and now most of them managed by countries in Europe or closed, because ISO is going to start other projects. And this is Campana Observatory, which is in front, a little bit north of La Silla. This is private, US private, because it's Carnegie. For many years had only one this is the largest telescope, 2.5 meters. But then 15 years ago, they started this project, the Magellan project, which are 2 telescopes of 6.5 meters each. And it has several partners like Harvard, MIT, Arizona, and Michigan. This is the place, and this is the telescope we Chileans like the best, because they work the traditional way. What that means is when I go observing there, I take my list of objects I want to observe. Nobody asks me, what are you going to observe? No, it's my idea. If I change my mind in the middle because I find something interesting, I can do it. Nobody cares. I am the king of the mountain when I'm there observing. This is not the case with all the new modern observatories where you have to send your data, the object you want to observe, and say how, and give exactly how to move the telescope and all of the instructions. And that is, we don't like it too much, because if you change your mind or you want to do something different, you can't. It's almost observing in space. When you observe in space, you have to give instruction to the satellite, and you can't do anything in real time. Here you can. And also the cooking is very good. They really make the best. They give you local sandwiches. I don't know, abalone sandwiches? Yeah, nobody else you can find it. For the night, when you observe. And the cook always finds you are too thin. You lost weight, you need. So, and here is the big, fantastic Paranal Observatory where Renz is coming. This is in the second region of Chile. It's the largest optical observatory in the world. It has 4 8.2-meter telescopes with really modern technology, plus a few other smaller telescopes. Here is at night, you can see the Via Láctea, the Milky Way there, with 2 Magellanic Clouds on the telescopes. I don't know whether it's going to, you can see this. Well, after the sun goes down, the telescopes, why is it? It's opening, you see? This is striptease of the telescope, they are, so that the air can flow through, and everything is the same temperature when you start observing. And because you really have to be worried about turbulence, and you don't want to produce turbulence that makes bad images in the telescope. But also we have to worry about the turbulence in the upper atmosphere, because the atmosphere could be completely clear and no clouds, but it has a turbulence. And that's why the pictures taken with Hubble, with the satellite, they are 600 kilometers from the surface of the Earth. There's no atmosphere there, and so the pictures are really nice and very good definition. But we learned how to solve that problem by sending a laser. For example, if I want to observe an object where the laser is, this green dot, then I send this laser, shoot the laser very close, and I form, this laser travels for 90 kilometers from the surface of the Earth, where there is a layer of sodium. And the sodium, with this laser, the atoms become excited and produce an artificial star. We know the form of that star because we fabricated it here. Let's say it's completely round. When it comes back, that image looks very not round. And then you apply a correction to that image to make it round. And the same correction you apply to your object you are observing. And this is done 30 or more times a second. And with that, we have been able to obtain fantastic images of the sky. And this is ALMA, a Chaknantor, which is a 66 antenna at 5,000 meters. This looks like a valley, but actually it's between 5,000 and 5,200 meters. These mountains here are 6,000 meters high, and there are several instruments there from Princeton, from Tokyo, from Cornell. And here we see the beginning of ALMA when they started constructing a few antennas. This is a really world project. It's ESO, USA, Canada, Japan, Taiwan. And Chile. Chile has 10% of observing time in every telescope here. And we define a Chilean astronomer because for astronomers it's clear, but for the other people maybe not. A Chilean astronomer is an astronomer who works in a Chilean institution. Doesn't matter which passport they have, you know. And actually the Chilean community is half Chileans passport and half the rest of the world, from Russia to Argentina, to Brazil, to Romania, UK, US, Germany, France. We have the whole United, all our students are foreign. And this year we received a student from Nepal, he is fantastically smart. The only problem the poor guy has is that he looks Chilean. He looks just a typical Chilean, so people tend to speak Spanish to him and he's just learning. So this is you just saw ALMA working, these 66 antennas work all together, and it's fantastic thing to see them move, you know, together, almost no noise, and each of them looking at the same object. Every time ALMA delivers data, it's a new thing, you know, we had not seen before. It's been a really fantastic contribution to our knowledge of the universe, thanks to that. So, and all of these projects, ALMA, Paranal, they run on the $1 billion, you know, area of cost or more. And to operate this is 10%, more or less, between 5 and 10% of the cost. So it's a lot of money. Sometimes when I go to ALMA, you don't have to go to ALMA to observe. The data is delivered to you. But I go with friends and sometimes with the business who are in business, and they say, who pays this? You know? I say, you know, the American government, the Japan government. What do they take from here? Because they are in the logic of, you know, you go and take something. I say, no, they are searching for new knowledge for the whole humanity, and some of them get it, some of them don't. But it's interesting because it's fantastic to realize that the countries all over the world are anxious to put money and resources there. And people want to work there, where it's very difficult. 5,000 meters, and at least in my case, I have to walk very slowly and, you know, don't do anything. For example, do not talk, because when you talk, you use a lot of oxygen, and it's complicated. But there are people doing hard stuff there. Just for, this is a meteorite in that picture. So, what we learned is the history of the universe. The universe started 13.7 billion years ago. The universe was very hot, made of fundamental particles. It started cooling down, and in the denser parts, the universe started forming stars, and the stars really fabricated all of the elements we know. This blue stuff was what the Big Bang at 13.7 billion years ago formed, and that is hydrogen and helium only. And all of the rest of the elements were formed by the stars. If you look at a galaxy maybe like ours, it has a neighbor, which is Andromeda, but it's at 3 million light years away. But then you look around that and you see more and more and more. That is not our galaxy, but it's an example. Galaxies live in clusters of galaxies who may contain tens of thousands of galaxies or more. In this picture, that one is a star, that one is a star, a few stars, but the rest are all galaxies of different types. Sometimes you have a galaxy which is really giant, and usually they are located in a strategic place in the cluster. So every time, most of the galaxies here, everything moves, and the galaxy, most of the orbits of the galaxy go close to it, and it eats it. That's why they call it cannibal galaxies, because they eat other galaxies, become giant. And this is our galaxy, la Vía Láctea. our galaxy. We are inside, so it's difficult to take a picture and see how it is. This is how we see it in the sky. The center of the galaxy is here, where is this brighter part. And the bright stuff is gas and stars that illuminate the gas. And the dark part stuff is dust. And dust is really small particles of graphite and silicates, and they are the stuff that stars are made of. And our galaxy contains 100 billion stars. Billion? Like, because 100 billion stars. And our sun is one more of those stars, just one. Nothing special. Most of the stars look similar to our sun. If we could go out of our galaxy, we can't, but if we could, we would see something like this. This is a different galaxy. It's a spiral galaxy, and we are here in the middle between the border and the center. And at 28,000 light years away from the center. So if a friend of mine who lives in a planet around the star near the center calls me on the phone, it will take, or send me a WhatsApp, I always say, I will receive it 28,000 years later. And then I answer, and it will be another 28,000 years. So this is our own galaxy, our city. And that's, you start seeing the problems of communication in the universe. There are all kinds of galaxies, and this is a kind of galaxy I was very interested for a long time, is that the radio galaxies. These are galaxies who not only have the stars of this is Centaurus and it's that looks like a fog. That's the stars of the galaxy. These stars are from our galaxy, and it has a belt of dust and these jets who are really very energetic. And it was a mystery for very long. What is the engine there producing these jets? And it was with the Hubble telescope that this was solved. And this is just a visualization of this. We looked at the center of a radio galaxy who had really huge jets, and discovered that there was a belt of stars rotating around nothing at really high speed, like 500 kilometers a second. And what is preventing the star from just, running away from this? Because if you make something to rotate like this, you have to exert a force so that they will not run away. And the conclusion was that there should be a mass of 1,000 billion times the mass of the sun. And there's no way you can put 1,000 billion stars there. So what is there is a black hole. A black hole, which is a really giant black hole, who attracts everything. A black hole attracts everything, including the light. That's why they're black. And the jets are produced when the stuff is falling into the... Here in our own galaxy, we also have a black hole. It's smaller, it's 3 million times the mass of the sun. It's on where this red cross is, and it's nearby, so we can observe the motion of the stars around it. The problem is that our black hole is on a diet because it doesn't have much to eat. And black holes become very bright and produce a lot of energy when the matter is falling into the black hole, because it heats up and produces X-rays and all kinds of high energy. But a few years ago, astronomers from Max Planck, here is the day, discovered there is a cloud that is going to fall into a black hole, and it already started. Actually, I was observing in Paraná 1.5 years ago, and I could see there was an astronomer from Max Planck observing the black hole, and I could see the black hole become bright and happy, having this something to eat finally. But aside from being nice, it is also very interesting because black holes have a lot of mysteries about them. And one of the things we have the opportunity to see matter starting to fall into a black hole, and maybe we can learn something more about this mysterious object. So, how do stars form? This is one question we would like to answer with ALMA, for example. The stars form when a cloud collapses on itself due to gravity. The center of the cloud becomes very hot, and when it reaches 10 million degrees in temperature in the center, you have nuclear reactions and you form a star. But the interesting thing about this is that you also form planets around it, and this disk of debris. This debris becomes comets and asteroids and stuff that is around the solar system, but any system, planetary system in this case. This is interesting because when I was a student, I was told that we were the only planetary system in the universe. Now we have discovered about 2,000. And it's very difficult because a planet is very faint compared to a star. So it's really not easy. And this is the maternities where stars are born. This is Orion, which is the closest maternity we have to the sun. And the stars are formed in this very dark nebula. So we cannot see in the visual, but that's why we have ALMA telescope that can cross that dust and really see how stars are born. Another question, is, are there planets, I just already answered, planets surrounding other stars? And the question is yes, we have been able to discover many, but it's very hard. This is an example of one method we use to look at planets, and these are all real stars. Huh? You have to look at all of them. Of course, we do it with a computer, but still a hard work to be lucky enough to find one, and here at the end is just a visualization, to find one that has a planet that is big enough, that goes around in the line of sight and covers the disk of the star for a while, and so that the luminosity of the star goes down and then goes up again. This is one method, and for example, the Earth here in this scale would be the size of the laser, the green laser. So, very difficult. The change in luminosity of the star would be almost impossible to detect. And I would like to show you this picture from the Cassini satellite that is going around Saturn to study Saturn. And this picture was taken when there was an eclipse. Saturn covered the sun, and they took that opportunity to take a picture looking inside the solar system. And unfortunately, there are some light, but you cannot see because this is our selfie, I say, the whole humanity. We are there. Maybe if you close a little bit the window, you can see it for a while. Unfortunately, that light shines directly into the screen. I know where it is on it. Yeah, I'm seeing it. Do you see it? There. Okay, I help you. There. There we are. This is our little blue planet. So, can you see this is from inside our own solar system? And it's still difficult to see the Earth. And what we would like to have is to be able to study this object and see if there is oxygen and water, and maybe the fact that the chlorophyll of the plants also, you can observe it in the atmosphere of Earth. If you can see, whatever you can see, even contamination. Maybe if you see contamination, you realize maybe they are burning fuel and it's a technological civilization. I don't know. But we are far from it. It's difficult now, but we will get there, I'm sure. And one of the instruments we have for that is this huge telescope, like the ELT. This is the European Observatory telescope being built in Cerro Armazones. It's a 39-meter telescope, huge. It's much larger than this room. Just the mirror. It's made of 900 mirrors of about 1.5 meters, hexagons that put together to produce. Look at the tracks here. It's really a huge thing. And well, one of the reasons is because we want to observe these small planets that may look like the Earth and may have life. There is another giant telescope, 24.5-meter telescope at Campanas, near, actually it is in the third region, and it has 7 mirrors of 8.4 meters each or something, and they make up a telescope of 24.5, and they're also looking for planets. And here is our sibling, the sun. We formed together with the sun, the planets. So we are made of the same stuff. We have different histories, of course, but we evolve differently, but we have the same age. And you can see the sun has activity. This is a movie taken by the satellite SOHO. It's a 1 week, and you see there are ejections, and this is normal. And I hope the sun continues to do this, because when the sun stopped doing this, for example, in the 1600, between 1600 and 1700, there was a little ice age when there was no summer here in Europe, and there was a lot of problems, hunger, and there were nothing to eat, and wars because of that. So we hope that the sun continues to behave. It behaves very well. We astronomers cannot wait for 1,000 years to see what is going to happen to the sun, but we can observe 4,000 stars just like the sun and see what they are doing. And we discovered that many of them have much higher level of activity, completely incompatible with life on Earth, for example, if we had the bad luck to be near a star like this. So our sun is behaving well for life. The sun has a 5,800 degrees in the surface, but 10 million degrees inside, in the core. And that there is a bomb there, like an atomic bomb that wants to make the star explode. And on the other hand, the gravity wants to make the star collapse. And the equilibrium between these two forces make the sun what it is now. But eventually, the fuel, which is hydrogen, which is becoming converted to helium, is going to run out of fuel, and the sun will die in about 5,000 million years from now. Before that, 900 million years from now, the Earth is not going to be possible to live in the Earth because there will be no water. The sun is going to become so hot that everything would be evaporated into the atmosphere. So we need to find another house before that. We have time, but we have to start, And then this is the future of the sun, It is, what is left in the center is a very tiny object, the size of Earth, very dense, all carbon. Somebody call it a giant diamond because it's carbon at very high pressure. And the interesting thing is that the external shell is ejected, and that shell is contaminated with carbon, oxygen, and nitrogen, who are very basic elements for life. They are part of our DNA. So you need a lot of little stars like the sun who had to be born and fabricate all of these elements and then die and leave as an inheritance all of these elements that will be mixed with other elements, other gas, and produce a new generation of stars that this time will have carbon, nitrogen, and oxygen from the beginning. What happened with the stars that are 8 times more massive than the sun? In that case, they can produce all elements until iron. And when they develop a core of iron, suddenly in 1 second, this star that lived from thousands of millions of years explodes in a supernova explosion, very energetic phenomena. And in the explosion, you form all other elements, including gold and copper and uranium, everything. So to be together and talking in this room today, we need to have had many generations of small stars that fabricated carbon, nitrogen, and oxygen before the sun was born. And a few of these big ones produce all the other elements we are made of. And that happened in the time before the sun and the planets were formed. This is the supernova what we can see now that exploded in our galaxy in the year 1054. It was recorded by the Chinese and also for the native North American natives. They made pictures because it was so impressive. It was like the full moon when it exploded and then faded out slowly. Now we can only see it with telescopes. And this beautiful picture going up to Alma. You can see these big cactus, I don't know, huge ones, and look like fingers, and this is our Milky Way. Just to say that the star fabricate everything, all of the chemical elements we know, and also very complex organic molecules, giant ones. And that is happening here and everywhere else in the universe. I always say as a joke, but it's not a joke, there is a nebula that's called Happy Hour, who contains ethylic alcohol. They also discover water.
Peace.
No, pisco not yet, but ethylic alcohol and sugar, some sort of sugar, very similar to our. So you will, some of our students want to know how to get there. Even, carbono 60 is a molecule that was discovered in a dying star in the Magellanic Clouds. And then it was fabricated in laboratories on Earth. So there is a really immense quantity of knowledge we can get from the universe. So, just satisfying our curiosity, but also we'll discover new things. The universe is very different to what we see in our world here, So things happen there that will never happen here. And that's why I see important to the preguntas inútiles, how we call it, and useful questions, or useless questions. Because usually when you apply for funds, they want to know, what is this going to be applied to? And and actually when you know what is going to be applied, you are working on a new vaccine, for example, it's very important, but it's really not new knowledge. But when you ask questions and go there for the discovery, you discover new things you were not expecting. And those are the really big breakthroughs in humanity. And so this is a photo, and it's not a mistake. This is a picture of my family with my son and my grandson. And I put it there because I want to emphasize that this is my story, my private story. It starts with the Big Bang. Now it ends with until now with my grandson. And it's also your story, everybody's story, everything's story. And I think, this is very important to know that we are the first generation to know about the story of the universe. And I think we're lucky. It's not perfect. Many things will change with time. But for now, we know more or less how this all happened. And I think, the fact that we are all, how do you call it, children of the stars? The stars are our ancestors. It's very important. It's a very strong message for humanity. And the fact that we are maybe small, we don't last very much in time, but we are the most strange thing that the universe has fabricated. The most complex. This is an evolution from simple particles to complex life with a conscience. And this is for me, it gives me a good feeling. We are the most sophisticated thing that the universe has fabricated, that we know of. And we have a conscience. We are the one who can put names to the universe, to things in the universe. And who knows, this evolution is going to continue. And I don't know whether humanity will be part of it, but I hope it will. Thank you.
Very nice. Very nice. Thank you very much. No, this was very, very nice. I did not know what she was going to present, but it's just perfect. Of course, if someone has any particular questions, I'm sure you'll be glad to answer.
If it is easy.
Even if it's difficult.
Okay, you answer.
We fake it.
You fake it.
Ah.
Yes?
I have two questions.
All right.
Two, okay.
First one, how you can be so sure that the universe was born 13.7 billion years ago?
Actually, it's 0.2.
And second, how long it takes for a black hole to eat one galaxy?
Forever. That is
One
it.
galaxy is a lot even for a black hole.
No, because
But you show us
Yes.
a galaxy being
Yes.
eaten by a black hole.
that's why I was saying that black holes
I
are
was a star.
yeah, it's a nebula, small nebula. But of course, stars fall into the black hole. But this is really weird stuff we're talking here. It's not simple things that where we can use our common sense, I think. Because this is strange physics. For a long time, I did not believe that black holes existed. No. Now I have to agree that they exist, but people don't really know what they are. We have the formalism in relativity that shows that one of the solutions of the equation is a black hole, and they have discovered it. But nobody knows really what's going on, especially because when you go into the black hole, there is no news that comes out. Nothing comes out. So it's impossible to know what is going on there. But in this weird world, when a black hole eats a galaxy, it goes on forever. We never see it disappear completely. But it's the formalism. In science, you observe something and then you invent an explanation using our theories and things like that. The theories are not touched, may change, so we don't know. And then the other question is,
How do you know the universe is
there are
13.7?
many observations that show, but we see the universe expanding. This is the simplest one. And so you can reverse the expansion and say, okay, this started 13.7. This is one way, and it wasn't very accurate. But then there are other observations that are much more sophisticated that came to the same conclusion. They were independently determined. And now we are fighting the second digit. I mean, it's 13.76. So maybe it is 13.8, maybe. But it's very good if you think that maybe 10 years ago, it was 15 instead of 13.7. So now we are fighting on the second. So, I think it's something that maybe is going to stay, it's being proven by different methods. And that is the important thing in science, to be independent. It's not the same thing. So I think it is, I'm pretty sure it's not going to change much. But I will not be surprised if tomorrow everything is different, because this is not a religion, it's science. And we scientists are very happy when things change because then we have more jobs. So we hope it will change a little bit. I think it's like a puzzle, and we have already managed to make the edges. I like to do puzzles, and you start with the pieces that are straight, and you do the edges and some parts. But you know, some pieces are not really quite, should not be there, and you have to continue. So it's a lot to learn, but I think we had advanced, and we, for the first time in more than 20,000 generations of human evolution, we're the first one to manage to do this. And I think this is a big success for humanity, because it's not a job for one person, but for the whole world.
Thank you very much. Thank you.
I'm going to go down because I want to see your...
No, in fact, maybe afterwards we could have a joint discussion. No, because this point that Professor Ruiz just made, that we are the first generation to understand why we are children of the stars, is something really deeply important. I keep repeating to my students, they look at you, it takes a while before the concept sinks in, but it is true. And it is a fantastic result, which we owe both to physics, astronomy, chemistry, to science in general. But let me start with something far less spectacular, but very relevant to the situation, because I'll show you the place where the new ELT, European Extremely Large Telescope, will be located. As unfortunately, the question of the light cannot be. This is one of the problems that we've never been able to solve. One of the several problems. If we could please close and let them be closed forever. Yeah, thank you. Very good. Very good. Okay, so I will now start, if I manage to see now, because I don't have any light anymore. Where did it go? Oops. They jump around when I do this. I apologize. I will. There we go.
È sempre quella.
Sì, no problem. Okay, here we go.
Ma non si vede.
Wait, we don't. Because. Wait.
Ecco.
It appeared. Plataforma ELT. Here we go. This is the top of Cerro Armazones. You can see, which is 3,050 meters. This is the end of the road, just been built. This is very recent. I was there the day before yesterday. And here in the background, you see, well, very beautiful, by the way, the shadow of the mountain over the Pacific Ocean. This here is the Pacific Ocean, and the other side there's Australia, right there, in the same direction, roughly speaking. And this is the top of the Cerro Armazones, which was cortado, right? It was cut by 18 meters or 20 meters of rock and a zillion tons. I don't know how many, but very many tons. Discovering that the density of rock here is 5, not 3, as I thought, because there's plenty of cobre, of iron, of everything. Yeah? And so it's a pity the Cerro itself was a bit ruined by this, but it is necessary to flat the top to make the room for this huge telescope. This, as you see, is like 3 soccer fields, to give you an idea of the dimension. This is not an Inca pyramid. This is the location where the cooling apparatus for the telescopes would be located, essentially. And this is El Camino Spiral, namely this road that winds around the Cerro and goes back to the base camp, which is down here on the left. And as you see, construction is doing very well. Let's say I was sitting here with the flag of Chile flying 2 days ago, and it's really beautiful. The environment is the desert of Atacama, of Chile. Humidity, when I was there, was 1%, not very humid. Not much water, and you get very, very thirsty. But of course, ideal for doing astronomy because it's all the atmosphere is of course extremely transparent. And yeah, this is the view from the top. This is the base camp, etc. So this I thought was quite inspirational. But now I shall move onto something somewhat different, which is another use that we have of the Atacama Desert. Not yet operational, but will be very soon, for doing a different type of astronomy. So far, you have seen a lot of very beautiful telescopes, meaning doing optical astronomy, which means to do astronomy in the relatively small window of frequency of electromagnetic wave or photons to which our eyes are sensitive. Our eyes evolved sensitivity in the same window through which the atmosphere is transparent. And we call it the optical window, which is extremely important. We have learned practically everything we know on the sky through this window. But in fact, the electromagnetic spectrum is infinitely wider, and there's a lot of information on the physics of celestial objects, also on other parts of the electromagnetic spectrum, and in particular at the high energy side, and in particular the very high energy gamma rays. This is interesting because it's a totally new window on the universe. I pause a moment because we will continue investigate in optical, infrared, etc. But at the same time, we will be able, using the splendid skies of Chile, to open up a totally new window, 3 decades of electromagnetic spectrum that have never been explored. And maybe lots of interesting stuff in there. You know, when you're a scientist, you want to do something no one has done before. You want to go and explore something. Okay, and so this is the idea. This thingy here is a gamma ray, a photon extremely rich in energy that falls onto the surface of the Earth. And then it interacts and creates something which we call a shower, creates a lot of electromagnetic particles. The electromagnetic particles move through the atmosphere and create some light. The height here is several kilometers, and the footprint of the light is about 140 meters. This is a cone of light that impinges on the surface of the Earth, touches the surface of the Earth with a diameter of something like 100 meters or so. So in theory, if you can collect this light, you have a lot of information on the primary photon, which is a photon which with an energy like 1,000 billion times the energy of the photons of the sun, which we see there, roughly speaking, 10 to the 12 electron volts. Now, this means that while we know exactly how the photons that come from the sun are produced through thermal processes, which we know very well, to produce a photon which is 1,000 billion times more energetic requires a very special physics that tells you something new about what is going on in the universe. So this is the interest, of course. And you have a telescope at a certain angle, and you see the light from a certain angle, and here it is. This is what you observe in the telescope. Don't worry if you don't understand everything, because it's a bit technical here. But never mind. The idea is that you have many telescopes down here, and you have a number of observations that are done at the same time, and eventually you position the arrival direction of the photon, namely of your celestial object, with a very good accuracy. And there are already a number of imaging astronomy Cherenkov telescopes in the world. There's one in Arizona, one in the Canary Islands, and one in the Namibia, and they do work very well. Here they are. They do work very well, but they are the first generation. We are aiming now to build an enormous step upwards, with the difference will arrive to the same depth in the universe as the ELT in the optical, and we will do it in Chile. This is the Cherenkov telescope array, the CTA collaboration that has various themes, of course: particle acceleration, probing the sphere environment, and frontiers of physics. The usual questions to go beyond the standard model. Incidentally, you have just heard a few days ago the Nobel Prize in Physics given again to the border between physics and astrophysics, because it was given for neutrinos, but neutrinos that come from outside the Earth, they come from the sun. And so, once again, it shows that physics and astrophysics are the same thing. And this discovery shows that there is something that must exist beyond the standard model of physics, which is an exciting time to live in. And CTA will do all these various technical requirements. Of course, to do astronomy, you need angular resolution, field of view, sensitivity, energy resolution, etc., all the characteristics of a telescope. And here we go. This is the weird way these telescopes are built. This, imagine, is the Atacama Desert, the surface of several kilometers, with many telescopes. We plan to place about 100 telescopes at least of various dimensions. These are the large telescopes, these are the medium, and then the small ones around. See, there's a 3-dimension of the. I will tell you in a moment. Yeah. We have found the location. So when, for example, an object goes off, there are many things that hit the atmosphere, but some of them are gamma rays that are collected by these telescopes. Some of which telescopes already exist, incidentally. And this is how it works. The light pool, namely the footprint of the light on Earth, falls with a diameter of about 100 meters, which is the typical telescope spacing. So you must be just able to cover the surface with many telescopes and have a detection area that can get the maximum number of images per shower. We have here the project, which has been ongoing for several years now. The price has slightly increased. It's of the order of 280 now, but it's a minor detail, of course. They always do price increase. And it's 27 nations so far. This is how it will be organized: 4 large telescopes inside, a number of maybe 20 or so medium-sized telescopes, and about 70 small-sized telescopes around. This difference in size and density of telescopes refers to the different energy of the photons we want to address, both low energy and high energy. The idea is to cover the largest possible energy interval that we can imagine. And we have a southern side and a northern side. And as Professor Ruiz was just saying, we love the southern sky, which is far richer in objects and in interest. So the southern side will be really the bigger one on a surface of diameter of 3 kilometers. The northern side will also be important, but more limited in dimension and number of telescopes. The reason to have the different telescope is that you want to have, this is the only graph I will show. This is a function of energy, and this is what we call sensitivity, namely how deep you go in the sky. So with the small, with a large telescope, you do the red curve there, and you see that it doesn't touch, it doesn't get down to sufficient sensitivity at the high energy. And then you use the medium telescope, 12 meter, and you get a little bit better. And then you use the small telescope, 4 meter, and you get up to here. So when you have the sum of all of them, you have a beautiful coverage over, as you see, more than 3 decades of energy. This is something quite important. There's not very many telescopes that cover this large energy interval in photons. So we need a site. We need a place where to put both the north and the south. And we had a competition. We had a worldwide competition, which was very tough, as a matter of fact. It was very tough. There were many contenders. For the northern side, there was Arizona and La Palma in the Canary Islands, and Mexico here. For the southern side, we had Argentina, Chile, and Namibia in Africa. The main advantage of Namibia, I must say, is there are no earthquakes in Namibia. Unfortunately, in Chile, there are earthquakes from time to time. I experienced one while I was there last week, not significant, but 2 weeks before, there was a very big 8.3 scale, so very significant earthquake. Unfortunately, earthquakes do not do nice things to telescopes, as you can imagine. It's better not to have them. But anyway, all things considered, we did the competition, and for the Argentina was the first to fall away from the competition in the south, and then Arizona, and then Mexico, and then Namibia. And now the choice is made. In the north, it would be on the La Palma Island, in the Canary Island, and in the south, it would be in Chile, close to Iso, in the Atacama Desert, close to Cerro Paranal, which is where we have seen the BLT telescope is. The Cerro Paranal is in a location very convenient because there's, of course, a very good road that goes up to it, but there's also the Ruta 5, la Carretera Panamericana, that goes relatively by, not too far. And so we have found on the property of Iso, Iso has been donated by the Chilean government a significant amount of desert, and there is a location which has to be flat, of the order of 1 kilometer, but there's plenty of kilometers of desert. No problem with that. So we have found the location. I do not have a picture, but it looks just like another piece of desert. There is nothing there at the moment. And so the consortium of CTA is done by a number of countries around the world. You see, Italy has Italy within us has a very significant presence in terms of full-time equivalent. We hope soon to have also Chile on board here. It would be very nice if Chile could enter. Obviously, since we are going to locate this, I tell Mr. Ambassador so that you know, it is important that since we are going to locate the telescope on Chilean ground, by definition, Chilean astronomers will have access to a significant percentage of data, both by themselves, probably better still in collaboration with the others. This is a totally new type of telescope. So we're now discussing a memorandum of understanding, an agreement on how to do this together with ISO on one side and the University of Chile on the other side. As you know, by definition, the ISO telescope, by tradition of maybe 40 years now, have a certain fraction of their observing time reserved for Chilean astronomers, and we should do the same. And of course, it would be even better if we could collaborate closely, namely have, for example, research students from Chile come and learn this new technique. This is a very new technique that is not yet available, if you want, in Chile. And then there's a lot of work to be done to actually build the observatory, of course, which will be open to Chilean firms, etc. There's a lot of maintenance. Something on technical design and prototyping. This is the large telescope, as I said, 23 meter in diameter. The mirrors are these hexagons that are about this big, all put together here. Relatively simple. The advantage of these telescopes, you do not need the high angular resolution that's requested by the advanced optics, of course, of the enormous telescopes. I'm going very fast here because I want to show you for closing how to build one of these telescopes. This is the medium size, and this is the small, which would be the one that requires many more units, about 70, probably would build 100. And there's several prototypes now being made. We in Italy are very proud because we have already built, designed, financed and built a new model of the SST, which this is the image, and I will now show you, if I can, how do you construct one of these things. Mr. Ambassador, please. This is on the basis of Etna. This is Etna Mountain. You can see it's a volcano, it smokes from time to time. This is the basis. It's the sort of thing we have to do. We'll have to do also in the Atacama Desert, the bases, but it's just a hole, no big deal. The basement is ready. This guy is waiting for the telescope to be delivered in boxes. Here it comes. We'll have to bring all these through Ruta 5 to the location. This was done, it work's been done in 2 months, actually. It was a splendid work by a group of Italian firms. Just 2 months, they finished the mounting of the complete telescope. So far you've seen the mechanical structure. This is the support of the optics, of course. And then the optic is put in here on top. Here, it is not yet there. Then this is the spider who goes up on top of the optics. While seasons pass and Etna further smokes, now the optic is mounted. And this is more or less finished. See the optics, here it is. This is the complete machine. All right. So we'll just build about 70 of those and mount them in this flat part of the Atacama Desert. Thank you very much, I think. I've shown you a new use of the 1 square kilometer of the Atacama Desert. We could produce extremely interesting new results in astrophysics, of course. Thank you very much.
Now we're invited to share a glass of wine.
Thank you. From Chile. Thank you. Open window. Difficile tenere l'attenzione di questa gente.
fatto vedere qualcosa di buono.
Perché prima lei ci aveva visto massacrato i bambini.
Sì, ho detto cose un po' banali. Ho visto prima la Monica.
Ma qua c'è Monica.
L'ho vista prima, adesso più.
Dico, come mai a Roma?
No, non lo so.